Imagine logging into your online banking app, but instead of your own account details, you see the exact same name and the exact same $0 balance as every other user on the planet. Without a mechanism to adapt to user input, software functions as a fixed set of instructions that returns the same result every time. It can display data, but it cannot interact with it. To actually function, computer programs require dedicated storage locations hidden behind the scenes to hold on to that unique, changing information. In C#, we call these storage locations variables. Every variable maps to a physical spot in your computer's memory. Instead of forcing developers to memorize complicated hexadecimal memory addresses, C# allows us to assign simple, human-readable names like customer age. These named memory locations are the structures that allow software to process and store unique inputs as they arrive. Creating one of these memory spaces in C# is a deliberate process called variable declaration. You're essentially reserving an empty box in the computer's memory. To claim this space, you use strict syntax. You state the data type, followed by the variable name. Next is variable initialization, where you assign an actual value, like the number 25, into that space. C# enforces strict rules for naming these variables. You cannot use spaces, and a name cannot start with a number. Professional developers also rely on shared naming conventions for clarity. They typically use Pascal case for larger structures and camel case for variables, where the first word is lowercase and subsequent words are capitalized. These rigid rules create a standardized language. When multiple developers are working on complex enterprise software, this consistency prevents chaos in the codebase. C# is a strongly typed language. That means you cannot just throw random data into an undefined variable and hope the computer figures it out. You must assign a specific data type. This tells the C# compiler exactly what kind of information is coming, how much physical memory to allocate, and what operations are legally allowed on that data. Whole numbers use the int type, but currency requires the larger decimal type and an M suffix for precision. Similarly, a single letter is a char in single quotes, while full words are stored as a string using double quotes. We also have the Boolean data type, which stores simple true or false logic. This binary storage is crucial for systems like login verification or checking if a payment went through. And sometimes data simply does not exist yet. If an employee hasn't been assigned a bonus, storing a 0 is factually incorrect. C# uses nullable types to explicitly represent an empty state. Enforcing exact data types acts as a safety mechanism. It prevents the compiler from attempting impossible operations, like multiplying a word by a number, before the program even runs. Perfectly typed variables sitting passively in memory still do not produce a working application. To do actual work, we use operators. These are the mathematical and logical tools that let us calculate, compare, and manipulate all that stored data. Let's look at a real-world software task, dynamically calculating an employee's net salary based on their base pay, an earned bonus, and their tax deductions. First, we set up 3 memory blocks for financial data. We declare them as decimal variables, ensuring each ends with the M suffix. Now we use arithmetic operators. We add basic salary and bonus, subtract tax, and assign the result to a net salary variable. This process is where beginners often trip up. Using a standard float instead of a decimal for money will cause rounding errors, and confusing the single equal sign used for assignment with the double equal sign used for comparison will break your logic entirely. Mastering variables, exact data types, and operators guarantees reliable data storage. It is the mandatory first step before a developer can begin building the complex logic that directs how an application reacts to different scenarios.